This is the second of a series of videos on p-hat, the sampling distribution of the sample proportion. And in this video, what we're going to look at is a couple of example problems. So the first thing, it would be good to review a couple of facts about p-hat, the sample proportion. And the first is that as an estimator, it has an expected value or a mean value equal to the true population proportion. In other words, it's an unbiased estimator if you take a simple random sample. The second one is that p-hat will be distributed approximately normal under certain conditions. And the conditions essentially are that the sample size is large enough. And we're going to use little n for the sample size. And the third fact is that the standard deviation of p-hat, that is that measuring the spread of the estimator, will equal to this particular formula, the square root of p times 1 minus p over n. And that's going to allow us to do a lot of statistics on it. So the first question is, let's look at this. The proportion of students who like baseball be 60%. And the question is what if you took a sample of 40 students and the true value is 60%, what's the probability that of your 40 students, more than 1/2 of them like baseball? So first of all, let's make sure that we understand what's going on here. In this particular problem, we know the true population proportion, and that's 0.6. And what the question is we're going to say, if we take a given sample, what's the likelihood that mu hat, or another way to say that is x bar, you can use either one of these symbols, what's the probability that x bar will be greater than 1/2? And sometimes instead of x bar or mu hat, they'll also use p hat. You can use any of those symbols. So let's go ahead and look at that problem. Well, the first thing that we're looking at is if mu is equal to 0.6 and n is equal to 40, then we know that mu of p hat will equal to p, or will equal to 0.6. That's going to be your expected value that you get anytime you take a sample. However, there's variabilities for when you take samples. Sometimes you get one number, sometimes the other, and we'll measure that by sigma p hat. And sigma p hat will be equal to the square root of p 1 minus p over n, and then we can just plug in the numbers. P is 0.6. So 1 minus p would be 1 minus 0.6, so that's 0.4. And the sample size is 40. We could just use a calculator to figure out what that number is. So that's 0.6 times 0.4 divided by 40. And then the square root of that. And that's approximately, we're going to round a little bit, that's approximately 0.77. The other thing we realize is that p hat will be distributed approximately normal. Not exactly normal, but close enough. In fact, we'll go in the next video, we'll talk about under what conditions we can be more assured of that. So let's go ahead and write all that down. So what we know is we know that mu p hat is equal to 0.6, and we know that sigma p hat will equal to 0.077. So now what we're going to do is we're going to try to find the probability that p hat is greater than 0.5. And since p hat is normally distributed, we can sketch this out, and the mean, remember that what's the mean? The mean is 0.6. And our question is if we sketch this in and this is 0.5, what's the probability that you get a number bigger than that? So that's essentially what you're trying to find. You're trying to find the area under the curve there. Now, this is a normal distribution, but it's not a standard normal. So the first thing we're going to do is we're going to convert to a standard normal. And a standard normal, another way to say that is we're going to find the z-score. And here the z-score, and that's going to allow us to use a z-table, which is in the back of almost every statistics book. Now, to convert to a standard normal, the basic formula to converting standard normal is z is equal to x bar minus mu over sigma. So we just have to think about how does that convert to p's. To convert to p's, that's going to be equal to p hat, or p hypothesized, if you can think about that, p hat minus p over sigma p hat. And that's going to be a formula. For now, you don't need to memorize this. For now, you can use your notes to work on that, but eventually that'll be kind of natural, second nature. And let's plug that in. So in that case, we get p hat minus p over sigma p hat. In this case, what we're going to do is that's 0.5 minus 0.6 over 0.77. And again, just use a calculator for that. That's 0.5 minus 0.6. That's a negative 0.1 over 0. Uh-oh, I messed up here. It's not 0.77. It's 0.077, so be careful. So let's divide by 0.077, and we get minus 1.298, 299 really. I'm going to round that to minus 1.3. Let's look at that and make sure that we figured that out. We know what the mean of the distribution is, and we want to find out what the probability, given that the mean was probability that is greater than 0.5, but we know the standard deviation. So we convert the 0.5 into a z-score using this formula, or these are the same formulae, they're just, this one uses the p's, and we get minus 1.3. So let's go ahead and draw the picture again. What we do is we have a normal distribution here. I don't have to draw it perfect, but the normal distribution where mu p hat is equal to 0.6, right? But we're going to convert that to a standard normal, right? And sometimes it's good to draw both of them together. You have one normal and you have another normal. Here this is 0.6. When we convert it, the mean is 0. This is 0.5. The z-score is minus 1.3. So your problem boils down into what is the probability that z is greater than or equal to minus 1.3. And that's equivalent to saying that what's the probability that p hat is greater than 0.5. And now you're essentially done. The only thing that you need to do now is you need to use a table. And let's look at the table. If you look at the standard normal table, then what you do is you go to minus 1.3. And since 1.30 you read over, and that's 0.968. No, 0.0968. Now that always gives you the amount to the left, 0.0968. So this region here would be 1 minus 0.968. So I could do that on a calculator. Let's see if I can do that in my head. That's going to be 0.9032. In other words, you have just over a 90% chance of getting a number greater than 1/2.